Hello. How's everyone doing today? Hope you had a good weekend. Welcome back to Intro to AI, Computer Science 3200. How are the volume levels out there? They should be fine. Okay. So, sounds good. All good on my end. How's everyone doing out there? All right. So today, assignment 1 is due tonight at 11:59 p.m. So in approximately 13 and a half hours. I'm starting to get the mad dash of questions from students having just started the assignment the day that it's due. So good luck with that. I'll try to answer as many as I can, but it's pretty obvious when someone has just started the assignment and they're asking questions about what the open list is today. So the next assignment is what we're going to talk about today, and this is an assignment that you cannot leave until the last day. Do not take that as a challenge to yourself. You are going to have 16 days to do that assignment, and you will need at least a week of that. This is the hardest assignment in the course. It's worth the most in the course, and you will also probably learn the most in the course from this assignment. So please, please, please ask questions often and ask questions early when it comes to assignment 2. So let's just get straight into it, because it's going to actually take a little while to get through this, but I'm going to be as thorough as possible. That way, hopefully, whenever I get a question about it, I can just say, go watch the lecture, right? That's the dream of any prof, is to not have to answer questions. All right, so here's assignment 2. It looks a lot like assignment 1, but there are some very, very noticeable differences. So, and by the way, this assignment will go live tonight. I'll have it for download at the due date of the last assignment. So the reason I'm not releasing it before that one is because it contains some of the code could be used for assignment 1. I don't want that to happen. So again, in our user interface, we have different maps. So these are all the same maps that you can choose from last time. But in the search algorithm, now we have A star. Okay, so there's many more search algorithms here. And so when we choose solution A star and we click and drag, we can see that now it's using A star. Okay, so it's using the A star algorithm that we went over last time to find the shortest paths. The big difference is that now we have many, many more options here. Okay, so for example, you can see here now that we're using diagonal actions. And so here you can change the legal actions from 4 directions to 8 directions. And you can see how the path changes when we go from 4 directions to 8 directions, right? And I'll get into the details of all this. I have a full PowerPoint presentation, and I'll be giving out that as a PDF about the assignment. And so you'll be able to refer to that or refer back to this lecture. The next big thing is that we have a heuristic function. So with A star, of course, comes a heuristic function. So there's 4 different heuristic functions here that you can choose from. There's the 8-directional Manhattan distance, the 4-directional Manhattan distance, the 2D Euclidean distance, and the 0 heuristic. So as part of the assignment, you're going to have to implement these 3 heuristics. The 0 heuristic, you just return 0. So that's no problem. And the last thing that's here as a new option is the object size. So we showed this off a little bit in previous lectures of the course, but in the previous assignment, your object, quote unquote object, or your agent, could only be of size 1, okay? Now you can have a 2x2 object, or you can have a 3x3 object. And you can see how, for example, the 2x2 path that we took through here is no longer legal when the object is of size 3x3. Similarly, if I go in here and I click a start here and a goal here, an object of size 1 can fit through this path. But if it was of size 2, it would have to go around, okay? And if it was size 3, then there'd be no path possible. And so that's what the object sizes are. And there's actually some really cool visualizations that you can do with the object sizes. Like, for example, if I go back to the medium maze, and I click like a start right here, and I click goal right here, and I do animate search, this is actually pretty cool. So you can see how the search happens in real time because the 3x3 object like fills up each one. So we can speed this up. And actually, if you set this to depth first search, this looks even cooler in my opinion. So you can get some cool visualization effects when you have the different object sizes as well. Okay, so now if we go back to instant path and we go back to default, then the only other thing that's different is that when I right click on the map, in purple is drawn the set of all states that is connected to the state that I have my mouse on. Okay, so for example here, you can only pathfind within the same color, so if I click it, essentially all the connected parts of the same color should be highlighted, right? So that's pretty intuitive what it means, but we're gonna have to compute this now. So if I do this with a 2x2 object, then what you can see is that the outlines here, like there's gray on the outside of this, and that's because the 2x2 object can only fit on the map if all the tiles underneath it are the same color. So this will make a little bit more sense if we have 3x3. So for example, if I have my object here, it can't fit there, right? It's not a legal position because all of the squares underneath the 3x3 object are not the same color. So if I right click right here, then only this purple is only showing the top left corner of the position of the object. Okay, so that's why some squares are gray here. It's because this is the position of the top left corner of the object for all the connected areas. And that'll be pretty obvious once we go into the details of the assignment. So that's a new assignment. The difference is that when you check, now the difference between 3200 and 6980 is that when you select student A star, there's another little drop down over here. So the 3200 students, you don't worry about this drop down. But the 6980 students have to implement bidirectional search. And we'll talk about what bidirectional search is at the end of the lecture. Okay, so that's the view of the assignment. Now, let's get into the slides because the slides are going to explain exactly what you have to do for this assignment to get this all working. All right, so lecture 6 slides, and again, these will be given out to you. This is on assignment 2. We're going to talk about grid pathfinding optimizations, and at the end, we're going to talk about bidirectional search. So, assignment 1 was given out to you to be an introduction to our user interface and the architecture for all of our assignments going forward. The algorithm for assignment 1 wasn't that difficult, but maybe how you incorporated it into our system was a little bit difficult. In assignment 2, you're going to be implementing A star, but again, the algorithm is not going to be the super interesting part, right? Because we saw the difference between BFS and A star is actually pretty minimal. All you have to do is sort the open list based on the F value. It's really not that bad. What the majority of the work in this assignment is going to be on is these grid pathfinding optimizations. And what I mean by grid pathfinding is when you have a grid system, like we do for this assignment, there's a bunch of optimizations that you can do that aren't necessarily applicable to an arbitrary graph search algorithm. And then at the end, we'll talk about bidirectional search a little bit because that's what the grad students are going to have to implement. So here's what's new in assignment 2. The A star algorithm, that's a new thing that we haven't done yet. We're going to have multiple object sizes. We have 8 directional movement. We have heuristic functions. We have connected sectors, right? Those purple things, those are going to be called connected sectors. And we have a bunch of pre-computation for optimization. Okay, so we'll go through these things in this order. So the A star graph search. First of all, we saw this algorithm in the last class, right? So this is the A search algorithm. But what I want to do for this assignment, because it's mostly about the optimizations and the data structures that we're going to use for pre-computing stuff. Yes, you're doing the A-star algorithm, but that isn't necessarily the biggest part of it. So what I'm doing for you is I'm just going to give you the straight up pseudocode for the search iteration function inside for assignment 2. And this is so you don't struggle with this part. This is basically the entire algorithm. And so you would have probably done a lot of this for assignment 1 already, but I just wanted to give it to you for this case and to help other people who maybe didn't get assignment 1 quite finished. They can do a little bit of catch up. So what's in the search algorithm, the search iteration part of the algorithm? And for those of you who maybe didn't watch the first lecture on the first assignment, what we put inside the search algorithm, the search iteration function, is whatever is inside the while loop right here. Okay? So again, the user interface for our assignment contains this while loop. And so what we put inside our search iteration function is just the inner part of that while loop. So first, inside the search iteration, we say, well, if the search is no longer in progress, we just return. Okay? So we don't find a path or whatever happened, either the path has been found or we haven't found one or whatever, then if the search is not in progress, just return. If the open list is empty, right? So if we've run out of things to search, then the search is done. And so we're no longer a search in progress. The cost is equal to -1. Oops, I put this down here twice. So just ignore that last in progress equals false. So that's the case where we've just run out of things in the search tree. And so that means if that is ever the case, then it means there was no path from the start to the goal. Now what we do is we grab the minimum f value node from the open list. If the state of that node is the goal state, after we've popped it off the open list, then we construct the path and set the cost for that node, and we set in progress equal to false. Otherwise, if it's not the goal, if that node's state is in the closed list, then we continue, right? Actually, that's supposed to be a return right there, so I'll change that in the slides. That's supposed to be return. If it's not in the closed list, then we add it to the closed list because we're about to expand it. Now, here's where I do the actual expansion, okay? So for every action in this.config.actions, now again, this is pseudocode. This exact line of code may not work in JavaScript, okay? So for every action that we have, we're going to generate the child nodes of this node. So, first of all, if this action is not legal, then we're just going to continue. We're going to skip doing this action. Then we're going to compute S, which is going to be the next state, right? Then if S is in the closed list, we can continue because if it's already in the closed list, we don't need to add this to the open list. Then we're going to compute the new G cost. So this new G here is going to be the G cost of the child node. So the G cost of the child node is going to be equal to the parent cost, the parent's G value, plus the cost of the action that got us to this node. Next, we're going to compute our heuristic function, and we're going to have a function called estimate cost, which takes in a starting point and a goal point. So this is the current state, which is this state x, right? So the state's x value and the state's y value. This is not the starting state, okay? This is the state that we just computed. Then we construct the child node based on all of these values. So we construct a new node based on those values. That's the child node. And then we add that child to the open list. Okay? So this is just the assignment. You can put other optimizations on top of this. And in order to get the fastest code in the class, you probably will have to put optimizations on top of that. So that's the whole algorithm, right? The rest of the assignment is a lot more work than just copying that from there into the slides. All right. So now we have the node class. The node class in this assignment has some new variables in it. So in black here, we see what the node class was before, right? We have an X value and we have a Y value. That's the state corresponding to the node. We have the action. Again, that's the action that generated the node. We have the parent. That's the parent that generated this node. But now we have some new stuff. When we were doing BFS and DFS, we didn't have to manually keep track keep track of the G cost. But now we do. So the node is going to have a G variable, and that's the G cost of the node. So that's the path cost so far to get to this node in the search tree. We also have an H value, and that's the heuristic value of the node. All right? And for 6980, in order to do bidirectional search, you may have to have extra variables here in the node class. But I'll talk about that a little bit more later. And remember that the child's G value is equal to the parent's G value plus the cost of the action. And also, if you want to, the node class could store the F value as well, and probably should. Okay, I actually think it does have that variable in there. All right, so that's what's changed about the node class. Now we're going to talk about actions. You probably know this already from assignment 1, but it's just a little bit more complicated in assignment 2. So I want to make sure that everyone's on the same page. So I'm going to explain the grid system and the actions from the very start. All right. So in our grid for our assignment, we have X, Y states, right? So X goes in this direction. So this is X. And Y gets bigger in this direction, right? This is Y. So in order to get from one grid cell to another grid cell, we have to take an action. And those actions have values, right? So before, we only had up, down, left, and right. But now we have the diagonals as well, okay? So in this assignment, we can have 4 directions or we can have 8 directions. And so what we do, for example, if we want to go up left, then that action is -1, -1. If we want to go up right, then that's 1 in the X direction and -1 in the Y direction, because Y decreases downward, right? So here we have those action values, but we can have up to 8 actions. So all the compass directions. Sorry, and the diagonals. But now we also have something a little bit new, which are the action costs, right? So in the previous assignment, all of our actions had cost 100. And the reason that they all had cost 100 is because they were all the same. So as long as they all had the same cost, it didn't matter, but I set them to 100. And the reason for that was I wanted you to get used to that 100 action cost, because now our diagonals have a cost 141. And the reason for that is because if you take a length 1 and 1 triangle, right? So we're moving from one square like this to another square. And so this diagonal here is the square root of 2, right? We just use Pythagoras. And so what we do is we multiply 100 by square root 2, and we get approximately 141. Yeah, so this down here is a typo. Let me just fix that real quick. Thank you for pointing that out in the chat. That is very appreciated. So there we go. So that was 141. So that's the reason, because it's 100 times the square root of 2. So now that we know what the actions are, in this assignment, legal action calculation is no longer just trivial. Okay, it actually gets a little bit harder, and this is where a lot of the optimization is going to come from. And by the way, I love this stuff. I live for these optimizations. And hopefully you're going to learn a lot in this assignment about just how fast you can make things run. So, just one second. I had a comment the first time I offered this course. It was actually a 4th year course. It was called Computer Science 4752. But that's no longer a thing. So it became a 3rd year course. But back when I did it the first time, someone told me that they came up to me and they said, I'm in the 4th year of a computer science program, and this is the first assignment that I did where I had to actually worry about how fast my code ran. And isn't that like a crazy thing? But it's funny because up until this point, this is a 3rd year course. So you may just be coming out of 2nd year, and when you're just coming out of 2nd year, you're still kind of struggling just to get the assignment to work, right? You're just getting the algorithm or the data structure to work. You're not really concerned yet with how fast is my algorithm running or how efficient is my algorithm. But this assignment is going to be, this is going to separate the childs from the parents, if you want to put it in in graph search term, this is going to be where you really start to care about that. And the legal actions is where we first apply some optimizations. But I'll talk about the optimizations a little bit later. So, legal actions. So an object can only occupy a region or a cell or a group of cells if all tiles underneath it are the same color, right? Because now we can have objects up to size 3 by 3. An object can only move to a space if the new region is also all the same color, okay? So I'll show you an example of that. An object must be entirely within the map, right? So if we have a 3 by 3 object and it has a size now, and so it could be partially in the map and partially outside the map, but it must be entirely within the map. And a diagonal move cannot allow the object to jump over, and I'll show you exactly what this means with an example, a tile of another color. All right. So, the first thing we have to do is look at object sizes and how they work. What I have here, oh, that's a laser pointer. I want a pen. This is my object right here, okay? It has an X, Y location. And when it comes to an object of size 1, the X, Y location is very, very obvious where that is, right? It's right there. It's the X, Y location. So this is an object of size 1. However, when I increase the object size, there's going to be multiple cells that it occupies. So how do we represent this object? Well, what we're going to do is we're just going to say that the position of this object is the top left corner of the object. So if we have an object of size 2 at this location, then this is where it occupies itself. Okay? So the position or the state of this object is the top left corner of the object. And that has to be carried out through the entire assignment. Has to be carried out that way. Similarly, if I have an object of size 3 by 3, it's going to take up more space, right? So here is where this object lives, at the XY location of the top left corner. Okay, so now we have to talk about the fact that objects can take up more than just one space, and so maybe they can fit in some places, and maybe they can't fit in other places. So because this object right here, it's occupying a bunch of cells that are blue, trust me, they're all blue underneath, then the object can fit at this location. So if I ask, can an object of size 3 fit at that state, XY? Yes, it can. But if I say, can an object of size 3 fit at this state? No, it can't. And the reason is because this square and this square are a different color. Okay? So just like we can only pathfind within the same color, now what we can do is we can only fit an object if it's entirely within the same color of the map. And so here, not all tiles are the same color. Over here, you can't see underneath it, but those are blue, right? These are all blue, and these are green. And so an object here cannot fit. So, legal actions now. These become a little bit different. So if I have, I'm just going to take for the example here, let's say I have an object of size 1 here, and it's at this XY location. So what are the legal actions for this, for an object at this state? Well, if we are right here, then the legal actions are as follows. I'm going to go clockwise. So I can move up. This is pretty easy, right? I can move up because this was blue and this is blue. I can move diagonally upright. That's fine. All of these are blue. I can move to the right. I can move down here. I can move down here. But look at these Fs. Well, this is pretty obvious. I can't move here because it's going from a blue tile to a green tile. And I can't move here because I'm going from a blue tile to a green tile. But why can't I move here? Right? And the reason is, if I were to just picture yourself pushing the object, sliding it from this state to this state, okay? So what would happen then, if I did that, is that it would be sliding across like this, and it would clip over or jump over this state right here. And so let me just get the laser pointer out, and let me discard these values. Okay, so if I was moving from this state to this state, and I slide my tile over like this, then it's going to jump over a tile of another color. And that is not a legal action. So diagonal moves can't jump over corners in this assignment. That is very, very important. So down here, for example, if we have an object of size 2, let's look at the legal actions that we can do. Well, we can move to the left. That's no problem. We can move to the bottom left. That's no problem. We can move down. But none of the other actions are legal. So let's look at why they're not legal. We can't move to the right because if our 2x2 object was right here, then it would overlap with a green square, right? And we can't do that. So moving to the right is not legal. Moving to the top right is also not legal because it would be on top of a green square. So that's not true. That's not legal. So we can't move from blue to green. We can't move up because then we would also be overlapping a green square. And now we have the same case of before, where if I wanted to transition this way, that's not legal because right here, this tile would be jumping over this tile, okay? So this is important. What we'd see is if we were sliding it up like this, then we would clip over this green tile, and so that's no longer legal. So even for objects that are of size greater than 1, we can't jump over tiles of another color, all right? And the last action, why can't we go down here? Well, in a similar way, this part of the object would be jumping over that green tile right there. So that is a illegal action right there. So let's look at an example where this actually comes into play. So if we have an object down here of size 2 at this location at the start, and up here we have a goal location that we're trying to get to, we can't make diagonal moves up here. We cannot do this, all right? And the reason we can't do this is because these diagonal moves would be jumping over tiles of a different color, okay? So in order to get from the start to the goal, we would have to take this path all around here. That's very important. So it might look a little weird when you're doing pathfinding. You're like, why didn't my object just slide up there like that? And the reason is because it can't do that. Now, similarly, you may look at this situation and say, oh, well, there's enough room to move diagonally here now, right? But actually, that's not the case. I cannot move from this tile to this tile because this tile would be jumping over this tile. So you can't move diagonally up here, but, with a big but, okay, you can move this way. So what you could do is move up, and then right, and then up, and then right, and then up, and then right, and then up. Okay? So that's how you would take it through there. So it is legal to go through here, but you would not be taking diagonal actions. See how that works? So you can't be jumping over these right here, and you can't be jumping over these right here. So the jumping over is important. So I'm just going to look at some questions here. If you can go north and east, then you can go northeast. Otherwise, you cannot. So let's have a look at that. That was my next slide. Good job figuring that out. So here's an interesting fact about legal actions. So in this situation, we can go here and here, but we cannot go here and here, right? And we know why we can't go there. So let's look at this. If we look at this right here, and now I know this isn't a proof, but it's an example that's good enough. If we look at the actions, the diagonal actions that are true, what we notice is a diagonal action is true only if both of these surrounding up, down, left, right actions, the cardinal actions, are also true. So here, we can deduce that this one is true because this one and this one are true. We can deduce that this one is false because this one is false. And we can deduce that this one is false because this one is false. Right? So only if the two surrounding actions are both legal is the diagonal action legal. And so we don't need to write the code that would detect the sliding over of other actions, right? So I know you were all getting worried, oh my God, how are we going to write that function? It's going to be slow. Well, the interesting fact here is that this one is legal because both of these two are legal. And it's really easy to compute whether or not the up, down, left, right actions are legal. So you can compute the diagonal actions based on the legality of the up, down, left, right actions. All right. So again, upright. So whenever you see two directions like this, that's upright. Upright is legal because up, then right, and right, then up are both legal. Okay? Down left isn't legal because left, down isn't legal. All right. And again, upright, so this upright, this even works with larger sized objects, which is really cool. Directly going diagonally upright is not legal because the right action is not legal. Up is legal, but right is not legal. So the great thing is that this works for objects of any size. So that's a really cool optimization that you can use in order to determine the legality of a move for any object size. Cool. Next, on to paths. So now when we're going to talk about paths, before, if I were to say draw the shortest path here, right, you may have said something like, well, go all the way to the right and then move up like this. Well, this is not a legal path. And the reason this is not a legal path is because from here to here, we are jumping over this green. Okay? So we can't jump over those greens, and so this is not a legal path. And so this is what the path would look like. You have to go from like the diagonal corner of one other cell to the diagonal corner of another. Excuse me. So we have to move all the way over like this, and since we can't diagonally jump up here like this, then we are moving from here to here. But once you have all the legal actions in there, then this is really easy to compute. And the cost of this path, then now, whereas before in the previous assignment, all we had to do was multiply the path length by 100 to find out our path cost. Now we actually have to store the g values like we did in the slides for the A star. And so here, the action costs, well, all of the four directional movement is 100. So we'd have 100, 200, 300, 400, 500, 600. But a diagonal move is 141. So now this is 741, 841, 941. And so the path cost here would be cost 140 or 941 from this start to this goal. Had another question. So in practice, if a four-directional move is not possible, then no diagonal involving that move is possible. Yes, that's the opposite way of saying what I just said. Now, keep in mind that if you were writing a video game, you could make it so that jumping over these things was legal, right? There's nothing about what we're doing in this assignment that says, oh, this is the way it has to be in your game. It's just that some of the really cool optimizations that we can do are possible because of that stipulation. So in this assignment, you cannot make diagonal moves that jump over things. Heuristic functions. All right. So because we're doing A star, we talked about heuristic functions last time, and heuristic functions are kind of the meat of heuristic search. So heuristic function, again, in case you forgot, it's a guess at how much distance is remaining from a start tile to a goal tile, or from a given tile to another tile. In assignment 2, we're going to have this function. It's called estimate cost, and it's going to take in an XY tile, and it's going to take in a goal X and a goal Y. And so we're going to have 4 different heuristics, and they're going to have different names. So dist, where you see this in the config, that's the Euclidean 2D distance. So you're going to run Pythagoras on these values. Card, this is the cardinal Manhattan distance. So it's a 4-directional Manhattan distance. So you will have to write a function that gives me the 4-directional Manhattan distance. Diag, this is the diagonal Manhattan distance. So you have to write a function that gives me the diagonal Manhattan distance. And 0 is done for you. It literally just returns 0. So again, just to go over the heuristic functions from last time, these are the 4 that we have. So if we have a start point right here at a given xy, and we have a goal point at a given xy, then this is the Euclidean distance. So this is the dist, okay? And yeah, so we would take, you know, the Euclidean distance, you just go look it up if you can't remember it. It's a square root of the x differences and the y differences squared added together. This is the 4-directional or cardinal Manhattan distance. So the way you compute this is you're at a given location. So we're at a current location here, x, y. We need to get to the goal. And so what you can do is you just travel in one direction until you reach the same row or column as the goal, and then you go the rest of the distance over, okay? And you don't need to compute a path for the Manhattan distance, right? You can compute this really, really easily, but I'm not going to give you the formula for that. I want to leave some of it up to you. The diagonal Manhattan distance is, remember, this is a heuristic function, so it does not take obstacles into account, right? So the reason this is jumping over here is because this is just a heuristic guess. It doesn't talk about, it doesn't look at any of the obstacles in the map. So here you have to travel downwards in a diagonal until you reach the same row or column as the goal tile, and then you go straight over, right? So you have to write the function that gives me that distance. So here, if you generate this path, then this is 141, 141, 141, 141, and then a bunch of 100s. And you sum that up and you return the diagonal Manhattan distance. And the 0 heuristic is just that. Now, someone out there, can you tell me which algorithm does A star become if I use a 0 for my heuristic? So if every heuristic is always 0, what does A star become? And I gave you that answer in the last lecture. Someone said breadth first search. Nope. That's not it. All right. Someone said depth first search. That's not it. And Allison says uniform cost search. Congratulations on being the first, right? So the reason, again, let me just go over that real quick. If we go to the blackboard, right? So what is A star? A star, oh geez. We have F of n equals G of n plus H of n, right? So that's our F value for A star. A star. But if we always have a 0 heuristic, then this becomes F of n equals G of n. And which algorithm do we take the minimum value of F of n equals G of n? That's uniform cost search. Okay? So these are all exam questions that you should be able to answer. Okay. So that's why A star with a 0 heuristic is uniform cost search. And your uniform cost search is going to give us that shortest path that we wanted, right? So you can debug your A star algorithm. So there's 2 things that can go wrong with your A star search. 1, the algorithm could be implemented incorrectly. And 2, the heuristic could be implemented incorrectly. And so what you can do to ensure, like, you can debug whether your algorithm is working by using a 0 heuristic. Because then, if your 0 heuristic, like, you know that the heuristic isn't broken because it's just 0, right? And the point is that with a zero heuristic, it becomes uniform cost search, which makes it run a little longer, but it will still give you the optimal solution. Let's go back to PowerPoint. Okay, so that's why we have the zero heuristic in there, just to be able to help you debug your algorithm. All right, the next thing, connected states. We talk about connected states, right? So if I go back to the assignment real quick, remember the connected states. If I right click, it draws, oh, this is the student A star. I need to click the solution in order to get this. So the connected states are all the tiles on the map that are connected to this one. Connected meaning that there is a path possible between them. And remember again that I'm drawing purple in the top left corner of the object, okay? So where you see this gap of size 2 down here, that's because the object can't fit down there. And if the object can't fit, then there's nothing drawn because there's no paths possible. So that's what connected means. Let's go back to the PowerPoint. All right. So two states are considered connected for an object of a given size if a legal path exists between them, no matter how long the path is. It just means that I can get from one state to another state. Now, I'm going to define a connected sector as the entire set of states in the environment that are all connected to each other. So in assignment 2, holding down the right mouse button highlights all the states that are connected to the clicked state. And the way that that works in the assignment code is that when you right-click on a tile, the user interface will iterate over every other tile on the map, and it will call your isConnected function, and if that returns true, then it will draw purple there. Okay, so that's how that works. And here's a little tip. Connectivity is transitive, right? This can be used for an optimization later to help you eliminate some if statements. So if A is connected to B and B is connected to C, then that means A is connected to C. That's the transitive property, right? So believe it or not, all those transitive, reflexive, commutative things, those actually end up mattering in programming. And it's because we can do stuff like this. So if A is connected to B and B is connected to C, then that means A is connected to C. So now we're going to look at some examples of connectivity, and then we'll go into how we can efficiently compute connectivity. Because it might seem really difficult to compute connectivity, right? Because if we need to know if a path is possible between two states, then don't we need to compute the path, right? So isn't this going to take a long time? Well, it turns out that no, we do not need to compute the shortest path in order to see if a path exists. So here's an example of two connected states, right? So this state is connected to this state because a path exists between them, and I've just drawn a sample path. I haven't told you how to compute the connectivity yet, but I'm just showing you an example that these two states of the environment are indeed connected. These three states, A, B, and C, they are all connected to each other, right? Because you can get from A to B, right? You can get from B to C. You can get from A to C. They're all connected. Okay, so these are all connected for size 1. They are not connected for size 2. Well, that might seem a little strange. Why aren't they connected for size 2? Can someone in the chat tell me why they're not connected for size 2? It looks like you can path between them, right? Like if there's a path of width 2 there, why can't you path between them? There you go. So Sergeant Pepper in the chat says because C is over land. Indeed. So for size 2, C would be covering blue squares and green squares. Similarly, size 3 would be even a worse case, right? Also, not only that, but B is outside the map. right? If we have an object of size 2 or 3, then it would be off of the environment. And so remember that we said that an object can only live entirely within the environment. But these are connected for size 2, right? So here, if we draw our objects of size 2, so C would be here, B would be here, A would be here. So the path from A to B, you could go up and then over, or from A to C. From A to B, we could come down here, right? And from C to B, we could come over here. Now, if we knew that A and C were connected, and we knew that A and B were connected, then we know that C and B are connected. Okay? They may not share like the same path, but they are all connected. But these are not connected for objects of size 3. So even though you can fit an object of size 3 right here, and you can fit an object of size 3 right here, there's no way to get from here to A, or from here to here. In fact, none of these are connected to each other, right? So you can fit size 3 objects in all these locations, but even though they're on the same color, they can all fit on the same color, right? And they're all here in the blue, like this is in blue, this is in blue, and this is in blue, and the blue is connected. It does not mean that those states are connected for objects of size 3. That's very important. And the reason is because no path can take you from A to B, B to C, or A to C. Similarly, like this start and this goal, right? They're not connected because they're different colors. That's really easy. So these aren't connected. A connected sector then is the set of all states. So if I right click here in the center, all of these states, right? All of these states are all connected to each other for size 1 object. Because I can path from any of these, I can go from here to here, I can go from here to here, I can go from here to here, right? And so these are all connected to each other for an object of size 1, so those are all connected. And I'm calling a set of states that are all connected to each other a connected sector. Okay, so let's look at computing connectivity. So remember what we said before, a diagonal move is only legal if both surrounding cardinal actions is also legal. This means that a path with a diagonal moves only exists if another path with only cardinal actions also exists. And I've already talked about that a little bit, I'll talk about it more later. Therefore, cardinal connectivity is the same as diagonal connectivity. And that's an excellent exam question, wink wink. Okay? Why is diagonal connectivity the same as cardinal activity or cardinal connectivity for assignment 2? And remember how we said that we can only go diagonally if we can go cardinally as well. And so, what this means, this is really cool. We can actually use a breadth first search or a flood fill, as some people may view this algorithm. We can use a breadth first search to compute which states are connected to each other. And I'll show you how we do that now. So here's the algorithm that we're going to look at. And I'll give the pseudocode for the algorithm later, but I'll just do an example of it first. What we're going to do, this is going to be a new grid. Okay? And we're going to call this a sector map. And I don't know why I don't have this here. All right. So this is a sector map, not a sister map. A sector map. Okay. What we're going to do initially is set all the values of this sector map to 0. And if at the end of the algorithm, any of our sectors are labeled as 0, it means that an object of that size cannot fit at that location, right? So if an object of a given size cannot fit on the map at that location, meaning that the cells that it overlaps are not all the same color, then it's not connected to anything, right? So 0 means this is not connected to anything. So what we're going to do is we're going to do a breadth first search like we said. we're going to start in the top left corner of the map. We're going to go here. And the algorithm intuitively is as follows. Starting from every location on the map, we're going to iterate over the whole map. So we're going to go all across all the X's and then down here like this. We can iterate over the tiles however we want. And the algorithm says as follows. If the cell has a 0 value, we're going to put a number in there, increasing by 1. And then we're going to do a breadth first search from that location, filling it out with that number. And so this is what this looks like, okay? We're going to start up in the top left, and we're going to give it, it says, oh, was that a 0? Yes. So I'm going to give it a value of 1. Now, I'm going to do a breadth first search in all 4 cardinal directions from this place, and I'm going to set all the tiles that I touch equal to the same number that I just set for this one. So I'm going to go out with the breadth first search, right? And I'm going to end up touching all of the blue tiles. So I give them all values of 1. Okay? Now it has to be the same color as well. So I don't go into the green here or the gray because it doesn't have the same color. And what happened there? Well, now we have computed anything in this grid that has a value of 1 is connected to any other cell in the grid that also has a value of 1, right? Because if I was able to go from here to here using a 4-directional breadth first search, then they both have a value of 1. And if I got from there to there, then it means that a path exists from there to there. And because my diagonal actions are only legal if cardinal actions are also legal to take me to that place, then the connectivity here is the same for both cardinal actions and diagonal actions. All right, so that's really cool. And that's actually the reason that you can't jump over cells of different colors. So here, anything with a 1 is connected to each other. Now, what we do is we just finished this tile, right? But we're iterating through every tile in the map. So on the next iteration, I go here and I say, does this have a value of 0? If it does, then do a breadth first search from here. But it doesn't have a value of 0. It's already been given a sector value, so I don't need to compute it. Next, I go over here. Does this have a value of 0? It doesn't, so I don't need to compute it. Blah, blah, blah. I go all the way across, so I'm iterating over the x's first. You could iterate over the y's, it doesn't matter. And then I get to here. And I say, does this have a value of 0? Oh, it does. Okay. So I'm going to take the last number that I used. I'm going to increase it by 1. And now I'm going to do a breadth first search from this location. So I do that. Okay. And my face is covering it, but there's also 2's up here, right? And so now any grid cell that has a value of 2 is connected to any other grid cell that has a value of 2. See how this is working out? Do you see where we're going with this? So now I keep iterating, and finally I get up to here and I see another one. Does this have a value of 0? Yes. So I set that equal to 3. Just increment that number. And then I do a breadth first search out from there. And look, so now I have the 3's. Now I'm going to come over to here. I keep iterating. And I'm going to skip all these because, I'm going to skip these because they have non-zero values. Then I get to another 0 value. And I set this equal to 4 and do a breadth first search from here. So what I have at the end of this computation is a sector map. And that sector map stores it stores integers. And now we can tell if 2 cells are connected by comparing their values in the sector map. And all we have to do now, after we've computed this data structure, in order to tell if a path exists between one state and another state, is look up its values in this 2D array and to compare whether or not they're the same. So we've taken the complex task of determining whether or not we have a path between two locations, whereas before we would have had to try and compute a path. By doing these breadth first searches, what we've done now is we have a constant time single lookup to compute connectivity. And that's like a huge cost savings. And so some people were asking me in assignment 1, why didn't your algorithm do any work if there was no path possible between two states? It didn't do any search. How did it know? And this is how it knew. Is because my solution for assignment 2 is my solution for assignment 1. Okay? So it had all of these computed sectors, and what I do before I look it up is I just say, hey, if they're not connected, there's no path. So don't do any search. And you put that in there as an optimization in yours as well. That's not in the pseudocode, but if you've watched the whole lecture, then you know that you should do that. Okay, so the algorithm I just described is right here. It's a function, it's going to be in your code, and it has to be implemented. It's called compute sectors. So what we do is we're going to set up this, I have m_sectors, which is the syntax from 3200 or 4300, so I just erased that. So this is the pseudocode of that algorithm. So on line 1, we have sectors equals grid map width map height 0. And that's just my way of saying, hey, we're going to have this sector data structure. It's going to be a 2D grid, and I'm going to set that equal to the map width and the map height. And I'm going to fill it with zeros. My current sector number, I'm going to set to 0, okay? So the sector number is the number that we're adding in here. So that's going to be equal to 0. Now I'm going to iterate over each tile on the map, and I'm going to say, oh, I have another m sectors. Okay, so I'm going to iterate over every tile on the map, and I'm going to say if sectors x, y is not equal to 0, so that means I've already filled this out, or if I can't fit there, so not can fit, then continue. So if I can't fit there or it's already been filled out, I don't want to fill out this particular grid cell. If instead it does have a value of 0 and it can fit there, then I'm going to increase my sector number, and I'm going to do a cardinal breadth first search going outward, doing this sort of paint bucket flood fill outward from XY with the given sector number. And I'm not going to give you the pseudocode for that. You know how to do breadth first search by now, right? And it's cool because you can do this breadth first search. There are really cool optimizations you can do on it, and that'll sort of, but this is only in the constructor for the class, so it's not going to affect your search running times, but there are efficient ways to do this breadth first search that I'm not going to get into. Then my isConnected function, if I want to tell if there is a path between two states on the map, all I need to do is return, hey, is sectors x1, y1 equal to sectors x2, y2? That's it. Really, really easy. Now, I also made a little mistake here. This is what it should look like, right? Because if this is not true, I continue. These ifs are not. Yeah, so someone just pointed that out in the slides, but right as you were typing that, I changed that. So what I meant by that is normally if a condition is true, you have things tabbed in, but I had a mistake there initially. And so if this is true, right, if the sector is not equal 0 or not can fit, then we continue, otherwise we continue on. So that was a mistake in style. So I would have lost points for that on the assignment. So the connectivity check, two tiles are connected if their pre-computed sector number is the same. So we can use this as a pre-check to see if a path is possible before computing it. And if the start and the goals are not connected, then no path exists between them. So now that we know that, that was all for size 1. What about for objects of bigger sizes? Okay, so what about connectivity for bigger sizes? If I take an object at this location and I look at an object of this location, these two are connected. right? These two locations are connected because an object of size 3 located at this position can path to an object of size 3 located at this position. However, this part is not connected, right? And the reason it's not connected is because it can't fit at this location. So, if we look at the environment, we actually have very few places on this environment where, so I've drawn an X here if an object of size 3 can actually fit there in the first place, right? So all of these other cells will end up having values of 0. And the reason for that is a 0 means the object cannot fit there. Okay, so let's look at the same example before where we used size 1, but apply our sector filling algorithm with an object of size 3. So we're going to start up here, right? We start up here. This was a 0, and an object of size 3 could fit there, right? Because we can draw it like this. So we put a 1 there, and then we do a flood fill outward. But when we do our flood fill, now we have to check if objects can fit. So we go out here, and the reason we can do this is because an object can fit here, and an object can fit here, right? So these get values of 1 in our BFS. Next, we're going to look outward from those. And so yes, all of these can go as well, because an object of size 3 can fit here, an object of size 3 can fit here, and an object of size 3 can fit here. Next, we go out more. Oh, but look at this. When we tried to go from here to here, we can't fit an object of size 3 there. So the breadth first search stops right there. Similarly, we can't fit an object of size 3 here. This is no good. This is no good. We can fit it here, so this is fine, and we can fit it there, so this is fine, right? So when we go outwards, this is what we'll get. And when we finish our algorithm, what we'll have is a little bit hard to see. We'll have 1s here. We'll have 2s here. Oh, so this should have been a 3 up here, depending on how we iterated through things. We have a 4 here, and we have 3s there, right? So now we have a new sector map, which is for objects of size 3. So in your code, instead of having just one like 2-dimensional array, right? So we have our sector x, y. Now, x, y. Now what you might want to have is you actually have to have a 3-dimensional array. So you have an array of sector maps. And then you would have sectors size x, y. Right? And so, oh, there's a y there, but you know what I'm saying. So now we actually have to have a sector map for each of our object sizes. If we want to, because connectivity is different for different object sizes. So when we talk about object sizes, 2 states on our map are never just connected. They're connected for a given size. And the connectivity is completely different for different sizes. All right. So let's look at some optimizations that we can do now. We've already talked about some, but there's even more. This is awesome. I love this stuff. So, the following optimizations will not affect the number of nodes generated, but will dramatically speed up the running time. So whenever we talk about any algorithm in computer science, so far in your computer science career, in your first and second years, probably all you've been talked about is the theoretical time complexity. So the big O notation, or the number of nodes generated, or whatever. That's fine. It's really good. It's more important to optimize your algorithm than it is to optimize your code. But once you have the good algorithm, then you optimize the hell out of your code as well. Because when you're doing pathfinding like this in a grid, if you put in all the optimizations, your final code might be 100 times faster than your initial code if you put in all the optimizations. So while you're not making a better time complexity, you are reducing the running time constant of how much time it takes to compute each node. And so that's what these speed optimizations are. So none of these optimizations are required for getting full assignment marks. But some of them may be required to get smooth paths while dragging the mouse. So if I go back to my assignment here, and while I'm dragging the mouse through my assignment, you can see that these paths are taking like 1 or 2 milliseconds, right? If I go up to a bigger map, like the StarCraft map, and I start dragging the path around like this, you can see that, okay, once I start making paths that are like the entire width of the map, then things start to get kind of choppy, right? We're no longer at 60 FPS. So here it's really smooth. Then when we start to get longer, okay, now it's not so smooth anymore, right? And the reason for that is that this GUI is running at 60 frames per second, and you start to see lag if the thing takes too long. So here, for example, this is taking 20 milliseconds, 28 milliseconds. And if I didn't have these optimizations in here, this may be taking 1 or 2 seconds. It's really important to do the optimizations. So back to the PowerPoint. And if you want to get the fastest time in the course, so again, we're going to be looking at the assignments, timing everyone's code, and I'll announce the winners of the fastest thing, and you'll get a D2L certificate, and it'll be all cool. All right. So here's a connected sector optimizations. For larger object sizes, we may have some tiles that have a 0 value. This means that an object cannot fit. So by pre-computing these values, we can use them later instead of doing the object size check to see if all of the underlying tiles have the same value. So what do I mean by that? Well, in our isLegalAction function, but if we do this all naively, every single time, let's say, for example, I want to compute if I can move an object of size 3, so here's my object of size 3, can I move it from this tile to this tile? So what goes into that computation if I do it naively? Well, first, I have to compute the new cell, which is right here. Then I have to iterate over all 9 tiles of this new 3x3 object to check if they're all the same. That's 9 if statements. That's really slow, right? Or what I can do is once I have the pre-computed sector map, then I can just say, hey, are these in the same sector? If they aren't, then I know that the object can't fit there, right? Oh, sorry, no, I just made a new optimization. So here's 2 optimizations. If it has a 0, it means the object can't fit. So when I'm just doing, the can fit function, I no longer have to look over all 9 tiles. All I have to do is look up in my sector map whether or not it's a 0, right? So anywhere there's a 0, it cannot fit. Anywhere there's a number, it can fit. So that's a can fit optimization. Similarly, my legal action optimization, I already did that one. I can do actually a move, so like an isLegalAction optimization. So an action is only legal if there's a path between them, and I've already computed if there's a path between them. So I can use the sector map to do a constant time lookup to see if a path is legal. Crazy fast. All right. Now, with that being said, in order to implement the connected sector computation, you do have to have your own isLegalAction function there and your own can fit function. So it's like I'm saying that once you've computed the sector map, you have a constant time algorithm for can fit and isLegalAction. But in order to compute the sector map, you also need to have can fit and isLegalAction, right? So what I did in my solution is I have 2 copies of those functions. I have the copy of isLegalAction and the copy of can fit that the computation of the sectors uses, which is slow. And then in my search algorithm, I have the isLegalAction and can fit, which uses the values in the sector map, which is really fast. Okay, so that's how I ended up doing that. All right, so I think I talked about this before, but I'll go over it again. Legal action optimization. We can do more to optimize our legal actions. We just talked about one of them. So the rule of no jumping over diagonals gives us an interesting property. A diagonal move of xy is only legal if both xy and yx are legal. And this property holds for all object sizes. And I actually already talked about this, and I don't know why I copied this over to these slides. So I'm just going to skip that. The isLegal function, the isLegal action function, is probably the most commonly called function in assignment 2. Because every time we go to do expand, we have to ask if an action is legal. So what we can do is we actually can use the pre-computed connectivity sectors to check for legal cardinal actions. Because legal actions are only legal if the source and the destination are connected. So that's what I said before, but I just wanted to have a slide. So this is a huge time savings by using that pre-computation. So again, diagonal move AD is only legal if AB, BC, and AD are also legal. So let's think about what this means. AB is legal if A and B are connected. And this is the same for all cardinal actions, okay? Up, down, left, and right. AB, BD, AC, and CD are legal if each of A, B, C, and D are legal. This means if A, B, C, and D are all connected, then A to D is legal. And connectivity is transitive, right? So if A, B, and BD are connected, then AD is connected. So if AB, AC, and AD are connected, then AD is legal. See how that works? So you may have thought, okay, if I want to compute whether or not this action is legal, I need to compute, okay, is AB legal and is BD legal? And is AC legal and is CD legal? So that's 4 checks. But we can actually cut down from 4 to 3 by using the transitive properly, because if A and B are connected, and B and D are connected, right, and AC and CD are connected, then AD is legal. So we can cut from 4 if statements to 3 if statements. And now another legal optimization plus, okay? Our environment is actually static. So tiles will have the same legal actions for a given object size every time you visit them. So what you can actually do is pre-compute all legal actions for all tiles and later just iterate over them, rather than generating them each time. And this will save a ton of time. So what we can do is we can have more data structures where we actually have in the grid, so the whole 2D grid now is a 2D grid of arrays, and inside here we store which actions are legal. So for example, here, if we're right here, which actions are legal from this cell? Well, only going down. But our environment never changes. So what we could do is pre-compute in a data structure, here are the legal actions from this state. Similarly, what are the legal actions from this state? Well, we can go right, we can go up, we can go down, and we can go down right. And so I can just pre-compute those. And whenever I go to generate the children of a node with this state in the future, I no longer have to say for every action, is this action legal? I can just look up the pre-computed actions that I did, okay? So this is a huge cost savings because we no longer have to check the legality. We can just pre-compute that. So I'm talking about all this pre-computed, all the pre-computed things that we can do. I have one very important rule for the assignment, okay, is that you are not allowed to pre-compute heuristics because heuristics are from one state to another state. And so if you think about that, in order to store all that, you actually have to have a 2D grid for each tile in the map. And that's a ton of memory. So there is no pre-computing of heuristics allowed. That's the only rule for precomputation. And no precomputing of paths either, obviously. So, a closed list optimization. So some people were very smart in assignment 1, and they actually implemented this as well. Closed lists store unique states, right? We're never going to be adding multiple copies of a state to the closed list. So each state on the map will either be in the closed list or not in the closed list. So what we can do for a big bump in optimization, in speed, is we can actually store a 2D array of Booleans, so true or false, which is the same size as the map. And that 2D grid, if it's true, it means that state is in the closed list. And if it's false, it means the state is not in the closed list. And so what we can do now is adding something to the closed list or checking if something is in the closed list is now a constant time check. We no longer have to iterate over the whole closed list and check that. Crazy good. All right. Open list optimization. So what you can do is you can use an array for the open list, right? And if you use an array for the open list, well, the thing I need to get from the open list is the one with the minimum f value. So what you can do if you use an array is to iterate through it and find the thing with the minimum f value. Or what I've done for you in assignment 2 is I've actually included a binary heap data structure, and the binary heap is a priority queue. Okay, so you can use an actual priority queue algorithm if you want, and that will speed up your search even more. Now, that's it for 3200. If it's 3200, you can stop here, okay? For the grad students in the course, for 6980, you have to implement bidirectional search on top of all of this, all right? So don't worry, it's not going to be that much work if you do it smartly and do it correctly. So far, we've looked at the case of finding a path from a start location, to a goal location. But what about if we wanted to do the other way around? What if we wanted to go from the goal to the start? Well, that's easy, right? We just call the goal the start and we call the start the goal. But what if we wanted to do both, right? So for example, if you're buying something on Kijiji or whatever on Facebook Marketplace and you're both 100 kilometers away from each other, wouldn't you maybe meet in the middle? Why would one person have to drive all the way across, right? That'd be kind of dumb. So what about both? So what bidirectional search is it searches from the start to the goal, and it searches from the goal to the start at the same time. And then the search stops when those graphs intersect. So intuitively, we can visualize why bidirectional search may save computation, okay? And I'll show a graph of this in the future. So search algorithms work outward from a start state, creating a radius of expansion, right? If you watch that red, it gets bigger and bigger and bigger. So which has a larger total area? One circle with a given diameter, or two circles, each with half the diameter? This one. And so these diameters are actually the exponent for the time complexity. That's the d. And so if we can get d over 2, so 2 times O of b to the d over 2 is way less than O of b to the power of d, right? So here's what bidirectional search looks like. We have a start location over here, we have a goal location over here, and we search outward from both until we get some overlap. And then this is a path, right? So that's pretty cool. Okay, so in bidirectional search, if we had done single direction search, what we get as the radius of expansion is this circle, right? The bigger circle. Bidirectional search, we get 2 smaller circles. And so the sum of the area of the smaller circles might be less than the sum or the large circle. Now, bidirectional search has crazy time complexity theory behind it that we're not going to get into. In some cases, it does better, and in some cases, it does worse. But your job is to figure that out for the assignment. So for an example here, for our assignment, this is our one circle, right? So we go from a start location all the way to a goal location. And the closed list area here is that's the idea of our circle, right? It has a diameter d, it has a path length, and we have a distance from start to the goal. So for example here, we have this path took 906 expansions, and 3,869 was the path cost, okay? But if we did bidirectional search, right? And there's no bidirectional search solution, okay? I was too lazy to implement that. So you're not going to be able to look at it. But if we did bidirectional search, what we would find is that we expand outward from the goal, we expand outward from the start, right? So this is expanding outward from the start, this is expanding outward from the goal. And if we add them up, we get probably fewer nodes searched. Okay. So in order to implement bidirectional search, it's not an entirely new algorithm, okay? It's just a modification to the algorithm that we already have. Now, I'm going to leave that up to you, because the whole point of this grad course is you are grad students and you should be able to go do some research and then implement that research, okay? So the algorithm is not going to be specifically given to you in the slides. The modifications that you have to do are as follows. You may use two open and closed lists. So maybe what you do is you have an open list for the start node and you have an open list for the closed or for the goal node. And you can add the start node to its open list and you can add the goal node to its open list to start. But you have to be very careful because the heuristic is backwards for the goal node open list, right? So back at the beginning of the lecture, I said that, You also may, if you don't want to use two lists, you could also think of how you could do this with a single open list, right? So if we use a single open list, then what we could do is add both the start node and the goal node to the open list at the beginning. So we're no longer just adding the start node, we're adding the start and we're adding the goal. And then we're just choosing the minimum F value from this single open list, right? But we have to be careful here because of our heuristic direction. We have to make sure that if a node was generated from the backwards direction, that we reverse the heuristic. And so be very careful of that. And we looked back at the beginning, I said the node data structure, you might have to have something more like a little bit more interesting there. You might have another variable if you're doing the bidirectional search. And this is what I mean by that, right? If your node was generated coming from the goal or coming from the start, your heuristic is actually has to be reversed. So we're also going to have a new goal test condition because we're starting at the goal and we're starting at the start. So we can't just say, is the state of this node equal to the goal node, right? Because we're already there. So what we have to do now, what is our new goal test condition? Is it when the closed lists intersect? Is it when the open lists intersect? I'm going to leave that up to you. So you're going to try these out, okay? And you're going to see what types of paths you get from them. And you're going to try them out in the assignment. All right. And and also, not only that, but if you have two open lists like this, or how do you expand your nodes, right? So maybe you can alternate taking the minimum F value from the closed list, from the open list. Let me restart that. The node expansion options, there are different ways that you can pick the next node to expand, okay? One could be, for example, I'm going to first pick the minimum F value node from the starting states open list. Then I'm going to pick the minimum F value node from the goal states open list. Maybe I go back and forth. Maybe I can do that. Or maybe I could check both lists and just pick the minimum F value from both, right? And if you do that, you might as well just have a single open list. But then you have to see where the two open lists intersect. And that check is a little more difficult if you have a single open list. Or you could use bounding strategies. There's a bunch of different things you can do. And for 6980, let's find the fastest solution. So for 6980, the prize comes for the person who has the fastest bidirectional search. All right. And what we're going to do now is we're going to look at a little demo of the bidirectional search. And after that, the lecture will be over. So here is a really excellent pathfinding search visualization website. And what you can do here is you can take the start and you can take the goal, okay? And you can draw in some obstacles. And if I do A star, over here on the right, it might be a little small on the resolution, but you can choose your different algorithm. You can choose your heuristic. This one is a little bit more involved than mine. But if I click Start Search, I go from the start to the goal, right? And this is start to goal A star search with the heuristic that we know and love. But over here, if I click, but the only difference is they allow skipping over edges. We don't allow skipping over edges, okay? If I click bidirectional and then click Restart Search, then what happens is you see the search coming from both the start and the goal, and then the path is found when those lists meet, okay? But whether it's the closed list or the open list, I'm not sure, okay? So that's how we do bidirectional search. And maybe the bidirectional search, in this case, it looks like it actually did some more nodes than it was supposed to. So that's bidirectional search. You can use that demo. It's in the notes. The assignment zip file is going to be uploaded at midnight tonight, okay? So you can start it tomorrow. And actually, it might be at some point this evening. I won't wait until midnight. You can do it you can start it this evening if you want. Please, there's a lot of programming in this assignment. A lot of programming. If you weren't following, the thing to take away from this is that you cannot start this the last day, all right? You have 16 days to do this assignment, and I suspect there'll be some people who come to me a day or two before the assignment is due saying, oh, I just started the assignment. Start this assignment immediately, especially the grad students. I know you're sick of this by now, but the algorithm is not the hard part for this assignment. And once you get through this assignment, the rest of the assignments are easier in comparison, okay? So this is the real hump for the course. See if you can get through this. You'll learn a lot. If you ever go into something like video game programming and you're doing pathfinding, then you know all about this stuff already, right? So it's super useful. I have used this in actual video games. And this course is all about not only teaching you the theory, but getting you to the point where you can implement it yourself, okay? So I'll stick around for a minute. If anyone has questions for the assignment, you can see the due date here. All right. So the due date is in 16 days. That is on 2020-10-15. Cool. And I'll upload those slides and this lecture immediately so you can start working on that as fast as you can. All right, well, there's no questions in the chat, so I'm going to go have my lunch. Good luck with the assignment, and as you know, I'm always around for questions, so feel free to send me questions on Discord or by email, and I'll respond as soon as possible. But please, do not leave this for the last minute. This is one of the hardest assignments you'll ever do in undergrad. Please do not leave it for the last minute, but you'll learn a lot too. All right. See you on Thursday.